Okay, I'm going to try to tighten up some of the stuff we did last time. In particular, tighten up geometric series stuff. Hardy's. Okay. Hardy's proof about finite decimals general base. Okay, then Hardy's so-called proof, pure repeating general base, and 4 Hardy's proof mixed general base. Okay. By the way, somebody left me a box of Sharpies with their banner number on it and a big capital A. I cross-referenced the banner number, that's what they use at FSW, and it was a student by the name of Joe, first name Joe. So Joe, thank you. I don't know why you just didn't give them to me. You know, I get apples all the time, not the computers. It'd be interesting to get some computers. But yeah, so thanks. And I got the hint. A and hexadecimal will be your next grade. Okay, so first, the proof about the geometric stuff, and it's just a minor correction or amplification. Okay, so proof about the geometric stuff, it's kind of an amplification. You know, last time I did a very, brief thing that went like this. 1 over R times R. Just move these up. And you get another one. Subtract. Let's go out, those go out. You filter out the R there. You do a division and you get 1 over R minus 1 over R to the 4th over 1 minus 1 over R. This pattern holds for general K, and this goes to 0, leaving you with 1 over R, or 1 minus 1 over R. Multiply that by R over R, and you get 1 over R minus 1. So you could do it this way. The limit as K goes to infinity of, let's use J equals 1 to K, 1 over R to the J equals 1 over R minus 1. Okay, so, and this translates, of course, to 1 to infinity, the infinite series. This is kind of interesting because R and R minus 1 are relatively prime. What's the standard notation for relatively prime, Bill? for the greatest common divisor. They have nothing in common, like 3 and 5. Two primes have nothing in common. Versus 3 and 9, the greatest common divisor is 3. Okay, these are relatively prime. You could also see that they're relatively prime. Schnackenberg can help me with this one. Two numbers are relatively prime. I think it must be if and only if. Two numbers, let's say A, B, are relatively prime if there exists a x and a y, x and y integers, general plus minus integers. And you can plug these in so as to get the lowest possible. A linear combination in integers, get that whole set, and the lowest one, we could use the Archimedean property to prove that such a number exists. That's one, they're relatively prime. So I think I can do r plus minus 1 times r minus 1, and that becomes r minus r plus 1, and that's 1. So I think that's a proof that r and r minus 1 are a natural number greater than 2. I think we have to go there. That they'll be relatively prime. We could do a little test of that. 3 and, let's say 4 and 3, 5 and 4, 6 and 5, 7 and 6, 8 and 7, no problem so far, 9 and 8. Okay, and I think it goes the other way too. R plus 1 is also relatively prime. Now, why this is of interest is, the pattern, the pattern of integer times 1 over b to the j, say, j equals 1 to infinity, equals a integer repeating kind of follows. As we are told, get pure repeating if the base and the denominator of the fraction are relatively prime. B base d of c over d. And so this is the pattern we got before. This is going to be 1 over b plus 1 over b squared dot dot dot, and you multiply it by an integer, and you get a repeating decimal, designated by this, where the integer is the stuff that's repeated. Now, technically, it's a little bit different than that. It's 1 over b to the m j equals 1 to infinity, times an integer is equal to the point integer, positive integer, you could do that, and this is also equal to integer without the line over b to the m minus 1. All right, so what we'd really like to do, and what I'd like to do, is get a derivation, a motivation for Fermat-Euler. Is it alphabetical, F, E, or E, F? Must be Fermat-Euler in chronological order. Fermat first, generalized by Euler. And we've just proved that this is really integer over relatively prime to be the base. Right, so you could start here and go back to here, I think. And then you could also do, well, this will be true. Let me see if I can get this. If the integer over bm minus 1 is equal to 1 over relatively prime to b. I come back over here. Right, so this would be like 1 over 7. And eventually that'll be true if and only if Bm is equivalent to some 1 mod of relatively prime to B. So you get a sequence of if and only ifs, and if and only if Euler is true, I'll just call it Euler, this is true and this is true, and then we get up to here. And we've proven that at least 1 over n, I think you can go with the 1 here, follows if it's relatively prime. Okay, so at any rate, that's a little clarification of stuff of last time. Next, number 2, I think I can do the finite, rule for general base. Hardy does it for base 10. I really don't think he does it for even his general case. Well, his general case is the product of primes. Right, his general case is the product of primes to a power of 1. A finite product of primes, each to a power of 1. But I don't think there's a problem in doing it for the general case. It's kind of a notational thing. And, you'd have to say, maybe I'll attempt to memorialize this a little bit. Hardy is, I'm going to go with very dated, because nothing like query-based, learning is going on in this chapter. That'd be 1, nothing like query-based learning, which I think I'm doing here. You do a bunch of examples, 1 through n is 2 through 13 or something like that. You figure out their prime or their decimal things in base 10, and then you make an hypothesis that the reason why 1/4 is 0.25 is because the power of a factor of 10, namely 2, is 2. You try that a few times, you say, gee, that seems to be holding. Can we prove that? And you evolve it. So for that reason, Hardy, he does some examples, but it's, to me, it's kind of creepy. It's not, it's very dated. And then the other thing is no calculators, spreadsheets, computer algebra systems. Is that it? Yeah, that's pretty good, I guess. Okay, you could also, JavaScript and Perl. Is that what they call that thing? No. Python is the latest. Python. Programs, get calculators plus programs, JavaScript, and you could say, you could probably go another one, 3, poor organization. It's, they just an example of poor organization. He has one proof that covers the three cases. And he jams it all in there, where you do one proof for base 10, and he kind of do one for general bases, product of primes to power of 1. And in both cases, you jam the finite decimal, the mixed, and the pure. And it gets all kind of, at least to my way of, looking at a well-written modern mathematical text, you should break it up into, 3 theorems, do each one individually with examples, and maybe, this is not so much in a lot of textbooks, but in my course, you do calculators. You see how well a calculator, a spreadsheet, can do this stuff. And I guess this is as good a time as any to pause. Here is a spreadsheet where, as you can see, let's see what this does over here. Maybe. A little bit bigger. Okay, so the base is 3. The number is 1/7. Okay, so this is representing 1/7 in base 3. That's what I get. It's a repeating decimal. The repeating part is 010212. 010212. You see that's repeating. It's not perfected, but you can, crunch this out and get, I wouldn't say it's, completely wonderful in a spreadsheet. You crunch these out, you do a division all the time. You can see the formula up there, and you can see it's referencing absolute reference to B1. That's what you're representing. And you take E9 right there. That's the number you want to represent. You do a division, and then you take the integer part of that, do another division of the difference, take the integer part of that. The integer part of that gives you the decimals in base 7. This is base 7. The other thing Hardy doesn't do at all, let's not lose sight of the main idea there. If just to learn about decimals, my estimation, you can't just do Hardy, read Hardy, and hope it's going to go in. A modern math student has to program it and has to see how, the issues with programming it, at least has to do a little foray into that in order to get it to go into their head, into my head. Let's go with that. For me to really understand these decimals, I have to, get it so I can train a very competent student. A calculator, a spreadsheet to do these conversions. Another thing I'll just mention here, another critique of Hardy. You could say this is not just within his dated, but a general critique. Critique of Hardy doesn't show convert to general base, ever, or he doesn't even, he does, I think, 1/8 base 2, but he really doesn't do that, nearly sufficiently, really at all. And, is it too hard or too weird or too much? I don't think so. Because we're going to do, I think, a pretty credible job over here. Well, let me just mention can do as generally get an integer when getting decimal, that's base 10, you generally get an integer, and we'll see an example of this in 1 second. And we know how to do repeat divisions to convert any integer to any base. All right, that was the 163 divided by 2. You get the remainders here. You do the Tarvanoi kind of thing. You get the remainders, starting at top, going down, and that is the representation of the number. He doesn't do that example of that. To do this in LaTeX, you could see is, the typography, the typesetting when he's writing this book in the 30s. Original edition, this being the 6th, was 1938, first edition. So, that kind of motivates why they jam everything together, and they have no illustrations. I think maybe they have a couple pictures in there with Gauss's 17 gun. I think they have a picture for a geometric argument. But, could they typeset a repeated division like I did the other day without LaTeX and the latest? I don't think so. So they can't do it. Could the latest editors of this thing, Heath Brown, Silverman, and I think old, what's his name, is involved with this edition, Wire, the guy who did Fermat's last theorem. Anyway, he's not credited as an editor, I don't think, in this. They credit just Heath Brown and Silverman, whoever they are. There's a whole last chapter, nowhere near existence in 38. It was added, written by Wiley, I think was his name. Anyway, so, that's another, problem with this. In order to do it right, you convert a number, a decimal number into a fraction. You generalize that to any base, any fraction into a decimal and any base. The finite case shows how you could get the conversion to any base, I think. Let me try this one next. Okay, so the theorem, Bn, that's your base, to 1 over m equals an integer, where positive integer, you do that. It's going to be finite. Let's clean this up here. Finite if and only if, finite base b, if and only if Bn times 1 over m equals an integer, and that's true if and only if m's prime factors, that's the d in our fraction, m's prime factors are a subset of B's prime factors. Doesn't bother to get into exponents, alpha, beta, gamma, and stuff like that. I think that's clear. We get a finite decimal if and only if b to the n times 1 over m, let's say finite 1 over m, base b, if and only if that's an integer, and that's if and only if m's prime factors are a subset of b's. Okay, I guess this is a proof. This seems kind of tautological. That's kind of the beauty of it. B's prime factors are in M. So there exists an n, which is max exponent of prime factors in M. They're going to wipe them all out, and the denominator is going to go, and you're going to be left with an integer. All right, so kind of obvious, the end of that. Next, 1 over m equals integer over b to the n. Point, integer, stop, finite. Maybe that's part of the proof. Put that part of the proof. That's a dot, a decimal, the integer over b to the n. It's finite. End of story. That's converting. That's not really the end of the story. You really want, I think you really need, next, convert integer to base b by repeated divisions. Okay, so I think we sort of did this. Let's say I want 1 over 3 times 7 in base 21. Let's make it a little bit more dramatic. 3 squared 7 in base 21. Right, I think that's claim finite and can get base 21 decimals. So that'd be a pretty, if we can do that, that's a pretty general case. Let's see what the answer is. I'll do a pause, and then I think we'll stop this one here. I'll do a pause. We'll go to my favorite website there. We'll put in base 21. Can we get this out? We need this in base 10. I think, I got to think this stuff out. I think I can put in this in base 21. I don't know. I'm going to have to take a pause. I'll load up, or let's stop it here. So next, website, and then Calc Crunch. I think if we can do this, we'll be on our road to the, a proof of the general case. Okay, so, are you with me in the back there?